Hello, Chem 2. Welcome to the last section for this chapter. In this section, we'll be covering, in this video, we'll be covering sections 6 and 7. But as far as the key concepts and objectives for this particular unit chapter, the last piece of puzzle today we're going to be dealing with in the last section, reaction mechanisms and how they can be used in order to determine the rate law of a chemical reaction. Administrative items, no different than the last one. You have the Chapter 8 exam still out there. Then there's Chapter 11 mastery. That's the optional. The Chapter 11 required. And then the Chapter 11 test is going to be live tomorrow, Tuesday. And you're going to need to get 75% on the required OWL in order to be allowed to take the Chapter 11 exam. Both of which are doable because of the number of opportunities you have to attempt the problems. Okay, so Chapter 11 is called the rate of reaction, or I refer to it as a chemical kinetics chapter. It's all about kinetics, the motion of the molecules and how it might change the rate of a reaction. We've done everything 1 through 5. We're going to do 6 and 7 today. 6 is really brief. 7 is a little deeper. Both of which, neither of which have that much math to them. So we got all the math out of the way last week. So just always share this. This is the table of all the equations and the like that I normally would give on the exam for this test, just to let you know what types of equations you need to be able to use and how they might be given to you. So this is how I would have given you the equations in class if we would have done this in class. My suggestion, maybe print this slide off so that you have it available to you when you're taking the test, so you have easy access to the equations at hand. So this last two sections, section 6 is all about catalysts and what catalysts are and how catalysts change the chemical reaction. So a catalyst is, and you learn this in biology, is any substance that is going to increase the speed or the rate of the reaction. But here's the twist, without itself being consumed. It does not change. It does not change at all. There's a matter of it starts and is kicked right back out of the reaction. Now, it may be involved in one of the steps where it gets to bond with something else and make a new compound. But for the most part, what happens is it's a opportunity for two chemicals that normally would not come together to come together a little easier. Second thing is what it has to do is it will change the pathway. Okay, now the new activated complex that is the go-between between the reactants and the products includes this catalyst. So that combination has a lower activation energy. So the hill on our energy diagram is going to be less. And normally it takes 2 or more steps. There's other steps involved during the catalyzation of the reaction. So here's 2 graphs. The red graph is the normal pathway that the reaction would take, and notice the activation energy is quite large. And then the second one is when you add a catalyst. And notice with the catalyst, there's 2 steps because there's 2 humps, and B, the highest amount of energy needed to get over the hump is smaller, which means if the activation energy for the catalyzed reaction is smaller, then more molecules will have sufficient activation energy in order to reach that reaction, and therefore the reaction will speed up. That was it on catalysts and what they do. Okay, so now for the more complicated portion of today's lecture, or this week's lecture, and it's all about mechanisms. When you hear the word mechanism, what do you think about? What do you think of when you hear the word mechanism? I know that when I hear the word mechanism, being that robot nerd, I think gears. I think one gear moving another gear, and that's a mechanism. In chemistry, it's not much different, but it's a series of steps that are involved. So when we're looking at a mechanism or reaction mechanisms, it's the path that the reaction has to take place, or the sequence of steps, the number of individual steps that have to take place in order for the reaction to take place. This example we've used a lot in this chapter. In this particular example, this is the reaction between carbon monoxide and nitrogen dioxide. And we've seen this a couple times over, how they bang into one another, they collide with one another, and the molecules are exchanged. Well, what's unique about this particular reaction is at high temperatures, the molecules have sufficient activation energy that they will collide with one another, and that oxygen will jump from the nitrogen dioxide to the carbon monoxide very, very readily. However, at lower temperatures, this will still happen, but it happens in a series of steps. It takes multiple steps for this to happen. It doesn't just happen with molecule CO colliding directly with molecule NO2 and the reaction taking place. What happens at lower temperatures is it happens in two steps. First off, two nitrogen dioxides collide with one another. And when the two nitrogen dioxides collide with one another, they much more readily exchange that oxygen from one of the nitrogen dioxides to the other. So you've got this nitrogen trioxide and a nitrogen monoxide. And then here's the cool part. That nitrogen trioxide, which is really, really unstable, that can very easily collide with a carbon monoxide, and then it can exchange the particular amount of material, that oxygen, over to the carbon monoxide, making carbon dioxide. So what's happening is, if you look at this reaction here, did I get my pen to work? Nope. What's happening here is that you have 1, 2 nitrogen dioxides on this side of the reaction, and over here you have 1. So these cancel out with one another. And then also, this nitrogen trioxide right here also is made in this step and then is used up over here. So that's why you get this to be the overall reaction. It's like adding together two equations, two mathematical equations. The same idea. If it's just the same material, is on the same numbers on both sides, you can cancel it out. So that's where you get this overall reaction. Now, there's a bunch of different types of mechanisms. The mechanism in general is steps. How many steps does it take in order to make the reaction take place? Well, in general, there are two major types of mechanisms. There's elementary, and then there's multi-step. Elementary is like this reaction was in the first case, where one compound bangs into another compound, one step, bam, it's done. Harsh reality, most reactions are not one-step reactions. Most reactions are not one-step reactions. They have to happen in a series of steps, and that's where it's called a multi-step mechanism. However, one of the really, really cool things about elementary or one-step mechanisms is they dictate or drive the rate law. Now, I know earlier on when we were doing this, I had said there's no way to look at a chemical reaction and determine what its rate law is going to be. Well, that was only partially true. If the reaction is a one-step reaction, a elementary reaction has only one step to it, then the rate law is going to be directly connected to the equation. So for instance, notice here I have one A in the reactant side. So if I were to double the number of A's, I would double the number of molecules that would bang into one another. So what I'm saying here is, if I double the concentration of A, then I'm going to double the rate. Well, that's a first order reaction. So that coefficient that's out front becomes the coefficient on, or becomes the exponent or the order for that compound. Here I have an A and a B. Same idea. There's one A and there's one B, which means I have A to the first and B to the first. Now let's think about this again. If I double the concentration of A, I'm going to double the number of molecule A's that are going to have a chance to collide with a B, which means ultimately, from a perspective of purely collision theory, I'm going to double the possibility of a reaction taking place. If I double the B's, I'm going to double the possibility of a reaction taking place also. And then there's a term molecular, they just go on and on and on saying that always, always, always you have this connection to the coefficients in the balanced chemical equation. Now, if this equation happened to have a 2 here, then the rate law with respect to A would be a 2. Now, truth be known, This only happens if it's a one-step reaction. If it's a one-step mechanism, then there's a direct connection between the coefficients and the rate law. However, I already said most reactions are not one steps, but each step of a mechanism, is a single step. So what we're going to do is utilize this connection of if this is the step, this is the rate law for this step in order to determine the rate law for a mechanism reaction. So first, before that, we have to talk about this concept of what's called the rate determining step. Essentially, what this means is whenever a series of steps takes place, a series of reactions take place in order to come up to the big reaction, one of them is going to be inherently slower. I often share the story that when I was in my first marriage, we would send out Christmas cards on a pretty regular basis. It was part of the chore, and I will call it a chore, that went along with sending out Christmas cards around the Christmas season. And you guys may do that also. Your parents may send out Christmas cards. Well, for us, we had the reaction or the process of sending out Christmas cards consisted of multiple steps. First off, someone had to take the envelopes and put the addresses on them and put the return address on them and add the stamp to them. And then somebody had to fill out the card. Well, my first wife, she was very much into sharing, or even to the point of oversharing what was going on in our lives on the Christmas cards. So it would be for every single card, it would be, Dear Aunt Betty, Calvin did this, Duncan did this, blah, 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 blah. And every single Christmas card took forever to fill out. The Christmas cards were not going to go out any faster until we sped up the rate determining step, or the slowest step. That was my ex-wife filling out the Christmas cards. Now, I proof positive 1 year, upon deciding that this was taking way too long to do the Christmas cards, I decided, or I suggested, that we swap roles. She goes ahead and fills out the envelopes, and I do the Christmas cards, knowing good and well that I was not going to do the long letter inside, personalized letter inside every single Christmas card. So every single one of them was like, love the Ferrins. Love the Ferrins, and that's what I did on every single card. Well, guess what? Since I sped up the rate determining step, the overall reaction happened faster. They got out faster. Now, they weren't as personal, but they did get out a lot faster. So the idea here is that if you, whatever you can do to increase the speed of the rate determining step, you're going to make the reaction go faster. Also, you can speed up all the other steps you want to, and unless those steps actually make the rate determining step go faster, it's not going to go any faster. Okay, so you're always driven, the rate determining step is always going to drive the reaction rate for the reaction. So in order to figure out what the rate expression is, first thing we have to do is figure out which one's a slow step, and then we're going to basically write the reaction rate for that step, and then see if any of the steps above it or before it play a role in speeding up or slowing down that step. Let me show you what I mean. So here's a idea of a mechanism. You've got 3 different humps. There were 3 steps involved in this reaction. Step 1 had a hump, step 2 had a hump, step 3 had a hump. This thing needed at least the amount of energy, activation energy, to make it happen. But you can see it happened in 3 steps. And very often, this is what you'll see, a little bit better than what we've described so far as one-steppers. So what we have to do, much like we did in the example earlier, is we have to eliminate any intermediates. Intermediates are anything that are made in one step and are used in a subsequent step, or things that are in one step and then are spit back out. So basically, there's things that in an algebra equation you cancel out. So let's look at what we have here. We have the D. It represents the decomposition of ozone, where you have ozone breaking down into its molecule of O2 and O, and then you have ozone again, another ozone molecule finding just an O. That's called a free radical when it's by itself. It's not in a diatomic state, and then it makes O2. Well, you add these guys up, then you've got this O and this O cancels. Those two O's cancel because they're on both sides. And you got two O3s on this side and 1, 2, 3 O2s on that side. So those two that got canceled, they're called intermediate products. Intermediate product is any reactant that is made, any substance that is made in one step and then consumed in a later step. Any reaction that is any component that is made in one step, an earlier step, and then is used in a later step. That's called an intermediate product. So when canceling out the intermediates, you're going to add these up. You got to cancel those out. So let's get to rates and molecularity. We already said that molecularity of the rate determining step indicates the rate law of the reaction. I mentioned that a couple times over. So here's what happens. Suppose in the reaction we've seen a couple times over that the first step is the slow step. Well, let's look at this. The slow step's rate law would be rate equals K times NO2 to the second power, right? So that means that this reaction is going to have a rate law that is NO2 to the second power. I can add as much CO as I want. It is a reactant. I can add as much CO as I want. This reaction is not going to go any faster because that speeds up a step that is after the slowest step. It would be equal when I was filling out the Christmas cards, and I did this one year, where I had my sons help me fill out the envelopes. One of those guys took care of the return address, slapped that on, one of them put stamps on it, and I filled out the cards. Guess what? My step went faster, but the overall getting the Christmas cards out did not go any faster. Now, there's a way to interpret these. If you don't want to think too hard, to go ahead and find the rate law for a reaction like this. And it works, I say 95% of the time. I'll show you the time it doesn't work, but here's what you do. You find the slow step, which we already said was the first step. Okay, you find the slow step, and immediately under the slow step, you draw a line. You draw a line in your mind's eye or physically, just so you can see it, and you draw a line under the slow step, whatever slow step right below, immediately below the slow step, you draw a line. And then what you're going to do is you're going to look at your reactants in your chemical reaction, that is your overall reaction, and count how many NO2s are there and how many COs are there above the red line. Above the red line, not in the overall reaction, above the red line. Well, right now in this situation, there's only two, or should I say there are two nitrogen dioxides above the red line, and there are no carbon monoxides. Well, that means, and here's where it becomes kind of cool, as a quick step that works, 19 times out of 20, is that NO2 is raised to the second power because there's two of them above the red line, and carbon monoxide is to the 0th power because there are none of them above the red line. So it's just a quick way to do that. This works under most circumstances. I'm going to show you in a little bit when it doesn't work and what you're on the lookout for when you think it doesn't work. Okay, well, let's try it again. Suppose the second step is a slow step. Suppose the second step is the slow step, not the first step, but the second step is the slow step, where you're going to do the same thing. You're going to draw a red line under the slow step. You're going to draw a red line under the slow step. And then again, you're going to count how many nitrogen dioxides are above the red line and how many carbon monoxides are above the red line. Well, there's two NO2s and there's one CO. So our rate law is going to be K times NO2 to the second power times O2 CO to the first power. Now, like I said, that works a very, very large percentage of the time. Not 100% of the time, but it does work a very, very large percent of the time. But what happens in what circumstances does it not work? What circumstances does it not work? Well, this is the circumstances where it doesn't work. Now look what we have here. We have a whole slew of uniqueness going on here. And that slew of uniqueness shows you one really cool thing. There's one thing here that you're going to be on the lookout for, and that's this double-headed arrow. Okay, if you have a reaction that has a double-headed arrow, what you want to do is you're going to handle this very, very differently and very, very, not necessarily mathy, but very algebraic. Okay, you're going to handle this very, very algebraic. What this double-headed arrow means, and actually it's a lead-in to our next chapter. It's a system that is in equilibrium, and what it means when it's at equilibrium is that the forward reaction is going at the same time as the reverse reaction. The forward reaction is going at the same speed as the reverse reaction. So the fact that the forward reaction is going at the same time as the reverse reaction, they're both moving. They're both moving. They're both going forward and backwards at the same time. So the fact that they're doing them both at the same time, if that double-headed arrow is above the fast step, is above the slow step, it's always going to be in the fast step. But when you have any issues, come to AP or college to talk about when the slow step is the double-headed arrow. There, that makes things a whole lot more complicated. But in this case, it's going to be above. If it's above the red line, if it's above the red line, so here's your slow step. This would be the line you're going to use that's above the red line. Okay, and it's goes forward and backwards. The double-headed arrow is above. Then we're going to do things a little differently. Now you have to do it algebraically. So let's walk through this. Algebraic step number one. We're going to look at the second reaction. The second reaction has the rate determining step as a slow step. So we're going to go ahead and write that particular rate law expression straight up. And then what we're going to do is write the expressions for the forward and reverse reactions together. And you see that in a second. Since the second step, since the first step has the forward and reverse, you're going to have two different rate laws, one for the forward, one for the reverse. Okay? And then we're going to combine things together to make sure you get just one single K. Let's go ahead and show how that works. So first thing we're going to do is write the rate law expression for step number two. Well, that's pretty simple. It's rate equals K2. They're going to use the term K2, meaning the rate law constant for the second reaction, times CO times O. So you look at the reactions again. I'm going to go back. For the second reaction, you have one CO3 and one O. One O3, one ozone, and one O. So we're going to have that as the normal rate law expression. Then what we're going to do is for the forward reaction, for the combination of the first reaction, we're going to have two different reactions going on. We're going to have one that goes forward and one that goes reverse. One that goes forward and one that goes reverse. One that goes forward and one that goes reverse. So we're going to call it one K1 and K negative 1. K negative 1 just means it's going in the reverse direction. Now, we know that the forward reaction has the same rate as the reverse reaction. We're going to talk a lot more about that in the next unit, but the forward reaction goes at the same speed as the reverse reaction. So what we're going to do is put those two together. K1 times O3 equals K negative 1 times O2 times O. So we're going to combine them together. Okay, see what we did there? We basically made this rate of the forward equal to rate of the reverse. So we're going to make them the same. Finally, the last thing we have to do is put it all together. So when I say put it all together, we know that if we take that second reaction, I'm going to go back, take this thing here, and we solve it for O. Okay, we're going to solve this equation, this last equation, for O. Because we don't have any O's in our reaction. We have ozone and we have oxygens, but we don't have any O's. So we want to replace this O in the slow steps reaction with whatever O would be reminiscent of this particular reaction down here. Okay, so we take that reaction, we get O equals K1 times ozone, K to the negative 1 times oxygen. And so we literally just made the swap. That means the rate of the slow step was K2 times ozone times O, and then we're going to replace this in where O is. So we take this equation here and replace it in where O is. Now, there's a lot of K's there. Really, since they're all constants, we're just going to merge them all together into one big constant. So we're just going to call it K, capital K, meaning the K2 times the K1 times the K minus 1, blah, 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 just call it a K. And when you do that, you get rid of this, this, and this. Then this becomes ozone to the second over oxygen to the first. Or, yeah, this is going to be kind of weird, ozone to the second, but oxygen to the negative 1, which means think about it, it's going to be slowed down if you have extra oxygen. It's going to slow down the reaction if you have extra oxygen. The reaction is actually going to go slower if you have oxygen, which is kind of weird, but it makes sense because if you go to the reaction, that first step has oxygen on the product side, and that would slow down the first step. Okay, so that's a lot of math, and I would suggest maybe you walk through that a couple times over before you try the required problem or the problem of the test that revolves around using this equilibrium step. It is a lot more complicated. It is a math thing. It is algebraic, very, very algebraic, since we did not do any true numbers here. It is very, very algebraic, but it's a way to get that rate law constant and that rate law from a mechanism. So let's really quickly look at this for one other concept. This represents another way that ozone is decomposed, okay? Because if you look at this, this happens to be if the ozone is in the presence of nitrogen monoxide. That's found in smog or pollution. So when there's smog or pollution, what that's going to do is going to change the mechanism. Okay, you still have the NO2 being canceled. You have an NO being canceled. You have oxygen-free radicals being canceled, and when they all add up, you still got the 1, 2 ozones and the 3 oxygens on that side. But those O2s, NO2s, and those oxygen-free radicals, those are my intermediate products, and we already talked about those in the previous one. Any reactant that is made in one step and then used in a subsequent step is called an intermediate product. But what about those other ones, these guys? What about these two? What is that? Something that is put into the reaction as part of the reaction and then is kicked back out later on. Well, that is a catalyst. Pollution will speed up the decomposition of the ozone layer. Nitrogen monoxide will speed up the breakdown of the ozone layer by acting like a catalyst. Any reactant, any substance that speeds up the reaction by being used in one step and being produced in a later step, that's kind of like backwards of an intermediate product. It is used in one step and then kicked back out in a later step. That is a catalyst. And there's my overall reaction. Okay, so take a moment if you want. I'm going to go ahead and hold off for a second. This is a checking up situation to see whether they can do this right. I'm going to leave this alone. This is a checkup, and if you need to see whether you did it right, the answers to this particular checking up is on the PowerPoint that's provided with this lecture, and you can see whether you did it right and whether you got the right reactions. But here we have a mechanism that consists of 4 steps, where the third step is the slow step. And again, there's no double-headed arrows here, so it should be a little bit easier. You're just going to be drawing a red line. So I hope that helps, and that is going to be the end of this chapter. What's next is for you to do the homework that's associated with Chapter 8. And then once you finish the homework for Chapter 8, we're in Chapter 11. Do the homework for Chapter 11. And then when you're done with the homework for Chapter 11, then you will be able to take the test or the exam for Chapter 11. It is labeled as Chemical Kinetics Exam Corona as a way to identify the particular test that you guys need to do for this. And again, you won't be able to see it until you get a 75% or better on the required AL. Well, I hope everybody is having a very happy, healthy spring. The weather is amazing outside, so I guess us being not in school is making it a little bit easier for us to enjoy some of the weather, even though you can't go wandering around the parks and such. But anyway, enjoy the wonderful, wonderful weather. I will see you hopefully sometime before the end of the school year. You guys will see me this week on the Flex Chats on Tuesday and Thursday from 2 to 3. Anyway, you guys have a fantastic day. If you liked what you saw today, again, hit that like button, subscribe if you haven't already, and hit the notification bell so you'll know when I update and send out new videos. This is the end of this chapter. So I hope you guys all have a very, very safe and healthy day. Practice that social distancing, and I will see you next time. And finally, always remember, never forget, Sig figs really do matter. Have a good day.